Alright, in this video we are going to appreciate the artery, arterial tree component of the vascular system. So when you're talking about the arterial tree, you're talking about aorta to the arteries, and then they take blood to the arterial is somewhere there, and then these go to the capillaries that then have an interaction with the tissue. One thing that you must know is that the aorta is highly elastic, and so you're talking about compliance mostly, which is as a result of distension. So how compliant is it to keeping the blood that is coming in? As you go down, you need to know that there's a lot of muscle here, so you are speaking of resistance. We talked about this earlier, and we will allude to it as we go on. So we will go through a few properties of these and appreciate them. The first thing that we're going to do is pressure. We note that in the aorta we have 120/80 as the pressures there, and then as we go about in the arterial tree itself, we have what is known as the pulse pressure. So what happens is that we have a forward movement of blood. There's also a backward movement, which we may not talk about at this point, but appreciate the fact that there's a pressure with which this blood moves in the arterial tree, and this pulse pressure is the difference between systole and diastole. So usually you find is at 120 minus 80. So it has a range of 8, 9, 10, 11, 12, about 40 to 50 millimeters of mercury, meaning you can actually find your diastole at 70 in some books as the average. The next pressure that I would like to talk about is a pressure, so this is the pulse pressure, is a pressure known as, I beg your pardon, mean arterial pressure. So the mean arterial pressure, this is the average, okay, it's the average pressure in the arterial tree, and it is usually noted as being from these properties, the fact that systolic component of the cardiac cycle takes about a third of the cycle, and the other component is diastole. So from here, we can calculate it as, first of all, the difference of SBP and DBP, which is PP. So it's a third of the pulse pressure, which we have already calculated, and we're going to add this to what you're going to see as the baseline, so to speak, pressure throughout, which is the DBP. So in short, you're saying that if this is systole, it's only taking about a third of the time, and the rest of it is diastole, which is about 80. So you're going to see an 80 throughout. Okay, you're going to see an 80 throughout the cardiac cycle, but from this 120, we're going to get 120 minus this 80, and we're just going to multiply that by a third of the cycle in order to get the consistent pressure that we think will be there throughout. Okay, so this is the pressure that we think will be there throughout the cycle as the mean arterial pressure. So again, mean arterial pressure will equal dBp plus a third of dBp minus systole minus dBp. Alright, having said that, we should know that the whole goal of this is to maintain pressure to the tissue. Okay, so this is the pressure that is required to be maintained for the tissue to stay okay. The next one that I'm going to talk about is it's another type of pressure, and this pressure is known as mean systemic pressure. Now, in the mean systemic pressure, this is the pressure that is in the arterioles, as well as the capillaries plus the venous lines, and it is on average 6.8 millimeters of mercury, and this is required to maintain systemic circulation when the heart is not pumping. So it maintains usually the venous pressure. So we'll come back to this, I guess, when we're doing the venous end of things. So while the MAP, mean arterial pressure, is for tissue, the MSP is really for the venous pressure maintenance. Okay. Another thing that I'd like to talk about when it comes to pressures is that the dependency. Systolic blood pressure is highly dependent on what is happening during systole. All right, so you find that if this is the aorta builds to about 120, and that's the one that is translated into the arterial tree. And if you don't remember what is happening here, you have a build-up from 0 to 8 to 80, and then contraction keeps on going until we get to 120, and this is in the ventricle. All right, so then it's really dependent on what is going on during systole, and aside from that, it also depends on how stretchable the aorta is. So we're talking about compliance. Okay. If compliance goes down, we see that SVT increases. Okay, take it really slow here. So if compliance goes down, it means that it's not able to stretch as much. So if something is not able to stretch as much, the area here is going to reduce, and there's going to be a lot of pressure due to blood being in a limited space rather than the space it would have been if it actually stretched. So again, if compliance reduces, you have an increase in systolic blood pressure. Secondary to this, you want to talk about DBP. Now, in DBP, if you remember, these are the arterials. They are highly masculine. And what will happen is that if there is contraction there that goes on, there's increase in the total peripheral resistance. And if there is increase in resistance, it means blood cannot move on to the venous side. So if blood cannot move on, it means you're increasing the amount of blood in the arterial tree when the heart is not beating. So if that happens, it means that what the pressure that you'll get in diastole will increase. So diastolic blood pressure is dependent on the total peripheral resistance, very much so. It's also dependent on the amount of blood that is trapped in the aorta. Okay, because the aorta will have to recoil during diastole to sort of push the blood forward to the arterial tree. Now, if there's not enough blood that is in the aorta, you find that the DBP is going to reduce. Maybe one more thing to talk about when it comes to pressures. The pressure has also been noted to reduce due to gravity. So the next thing I want to talk about is gravity. So for gravity, you see that pressure in the vessels that are below the heart will tend to, let me say that again, pressures in the vessels below the heart level will tend to increase. Okay, and if it's above the heart, you will find that there is a decrease that goes on. So this is very specific. For every centimeter, you'll find a 0.77 millimeters of mercury pressure increase or decrease. So if you're going to talk about an artery that is, you're measuring about 50 centimeters above the heart, you will talk about it being, so let's say if the heart pressure at that point is 120, you will say 120, and then you're going to say 0.77 times 50, because for each centimeter you want to reduce it by that much. So that's going to be your final pressure at that point. If you're going to calculate in the foot, which is about 150 centimeters below the heart, and you've been told that in the heart there's a pressure of 100, you're going to say 100 plus 0.77 times 105. So you will conclude that is about 180 millimeters of mercury